All right, well, good evening, everyone. You see, we've got a good group again tonight. That's always a good thing. We're going to be looking at Chapter 8 tonight, which is on propagation. It's a real nice follow-on to what Gary covered last week for over antennas. So it's got to come out of the antenna and somehow make it to the other side of the world, and that's what propagation is all about. So I'll move right into the presentation. Here we go. I always put my contact information on the first slide, and gotten emails and phone calls from people, all of which are welcome. Now, as we're moving into or upgrading to your general class license, the thing that's going to be new is access to the HF frequencies. So the real focus relating to propagation here is going to be on the ionosphere, which is the magic that makes HF work around the world. So we're going to answer the question, how do we get from a transmitter to a receiver a long ways away? So this is just kind of a preliminary slide indicating that there's 3 ways to get a signal from hither to yon, as I like to say, from my transmitter to your receiver. And those 3 ways are Skywave, which is leaving your antenna, going up to the ionosphere, being refracted back down, and coming down on the other side of the Earth, a couple 2,500 miles away, let's say. So that's going to be the main focus for tonight. The next version of propagation is what's called space wave, and that's basically line of sight. You're all pretty familiar with that, having worked with HTs and 2 meters. And then the third one is called ground wave, and that's where signals will actually hug the ground, actually kind of curved. This shows it straight, but the ground wave goes out from the transmitter and hugs the Earth, but it doesn't go very far, just a couple hundred miles at most. So we've got line of sight, ground wave, and then sky wave, which is really where all of the fun is. So the ionosphere is the central theme of this chapter, and I saw something coming home one day that really blew my mind, and that was this. It's a bus called the Ionosphere. So the question is, does anybody want to come along for the ride?
Yes, yes.
Yes, yes, yes. It almost looks, these are actually power lines up above, but it looks like some kind of an antenna, so that would even be better. So the answer is probably yes. If you're interested in awards like Worked All States, you have to go from, well, we're on the East Coast here, South Carolina, but if we want to make it to California, we have to bounce signals through the ionosphere in order to make it. Or if we want to work Germany or Japan or China, that all is Ionosphere doing that for us. This is actually a bus touring company based in Anderson, South Carolina. I don't know if you knew that, Gary, but they're based here. Yeah, I had to take that picture when I saw it. And the ionosphere, I'll mention, goes up about 300 miles. So we won't be traveling much more than 300 miles in our magic bus. So the ionosphere, the region that is so helpful for us in HF, starts about 30 miles and goes up to 300 miles. You'll see all different numbers for this. Some will say 300, some will say 500, but it's roughly 300. Now there's one type of radiation that we call ionizing radiation, that's ultraviolet light and X-rays, actually have the ability, the energy in that radiation can knock electrons away from molecules of air, and that leaves a positively charged ion and a free electron. Thus the term ionosphere when this happens way up in the air. And then radio signals are refracted. We're going to have a little bit more on refraction coming up, but radio signals are refracted by changes in electron density in the ionospheric regions. This is just an introduction. The Kessler intro videos were really excellent on this. I hope some of you had a chance to look at those. Another feature of the ionosphere is it protects us Earthlings from the dangerous radiation from the sun. It blocks most of the ultraviolet and X-ray, because we wouldn't get along well with that. So here's a scale diagram. I had a friend that brought a globe to a ham meeting, and then he had stuck to that globe some playing cards, and he was trying to demonstrate the relative thickness of the ionosphere as compared to the Earth. And that's shown pretty well in this diagram as well. So it's compared to the size of the Earth, it's pretty small, not up very high. So the Earth's diameter is about 8,000 miles. The atmosphere is about 30 miles thick. That's the air we breathe, and the next couple of layers. And then the ionosphere starts above that. There's specific regions, and I'm not sure what possessed the pool committee to change this, but this always used to be called layers. But in this entire chapter, it's regions. If you looked at the old material, I didn't want you to be confused. And what happens during elimination by the sun, these ion layers will appear, or regions, starting out with D, and it goes to E, F1, and F2. This is on the daylight side of the Earth. And then at night, they kind of collapse, leaving only the F layer. I'll have a better close-up of that. But just getting you introduced to the concept. So we have a day side and a nighttime side, or dark side. We have regions appearing and disappearing as the Earth rotates. And these early diagrams show everything as nice, smooth, even arcs. They're really not. It's kind of a confused mess up there. And that's going to be a good thing when we get to the last section of this chapter. One other thing that this demonstrates, on the daylight side of the Earth, we're in sunshine, and on the nighttime side, we're in darkness. And the terminator between the two is called the gray line. We're not going to really be getting into gray line propagation too much in the general class, but you've probably heard the term and just wanted you to know what it was. That means somebody at this point on the gray line, somebody on this point, would probably have really good propagation. Now we're getting into some more detail on some of the heights. So we see Mount Everest, that's this point over here. And airliners fly a little bit higher than that because they don't want to run into the mountain. Then the D layer is where the ionosphere begins, 30 to 60 miles. The E layer is the next one up. Then we get to the F1 and F2 layers, and this is the space shuttle. It flies about 250 miles up. Now here's a little bit more on what's happening with the ultraviolet and X-ray. Ultraviolet is the primary source of ionization. So these lines coming from the sun represent the UV and X-rays, which I told you was ionizing radiation, because it can actually knock electrons loose from the air molecules. The D region, some people call that the destructive region, remembering the letter D, tends to absorb lower frequency signals when ionized. So in a way, that's a very good thing that it goes away at night. And then I've got a few slides on some of the characteristics of each of these layers. They're too small to read, but the important thing is the D region here is the lowest one. And again, anything that appears as a pool question will be in blue. So if you're going to go to sleep during the slides, sleep during the black text, okay? So D region is closest to the Earth. It's only present when illuminated by the sun, and it completely goes away at night when no UV is present. Absorption is an enemy of HF communications, particularly on the lower bands. So the absorption increases in the daytime when the UV is more intense, and it's the most absorbent of signals during daylight hours below 10 megahertz. So we're talking 40 meters and 80 meters and below. That's why propagation during the day is usually very poor on those bands. It gets much better at night, and when those bands can go long, as they say. So that's a D region. And here we've got some of that information in the context of the way the wording is in the pool. Long distance communication on 40, 60, 80, and 160 are much more difficult during the day because the D region absorbs these frequencies during daylight hours. E is the next one. E is a real interesting layer because I'll skip to the bottom first. It's got some very unique propagation modes. We're going to be talking a little bit about E-skip or E-scatter. Meteor scatter, which we don't really get into in the general classes there, but there's literally hundreds of thousands of small items of sand and small rock that enter our atmosphere every day, and you can actually bounce radio signals off of those trails. They create ionized trails in the E layer when they burn up. And there's one case where we have enhanced VHF propagation, especially near the poles. We're going to talk about this. These are all E layer effects. Like the D region, develops during the day and disappears at night. Now the air is less dense at this level compared to the D layer, so it will last longer after sunset. And being higher than the D region, we have a longer hop. We can go up to 1,200 miles with a single hop in the E region. I'm going to be switching between regions and layers, so you know it's the same thing. There's a lot more on the E layer when we get into the extra class. Now the F region, this is the region that we really like the most because we can talk the furthest. 100 to 300 miles high. During the day it breaks into F1 and F2, shown here, F1 and F2. At night it returns to a single F region, combines. It varies with the times and seasons and solar activity, and it's the longest single hop region, up to 2,400 miles. Now the stronger the sun's illumination, the higher the F2 region. So that would imply that at about noon local time, you should have the highest F2 region. Here's we're getting into a little bit more on refraction at this point. The prism analogy you've all seen in high school science, I'm sure. Light being split out into its component parts as a result of passing through a prism. What's happening in the case of light is that as the light impinges on a denser part of the prism, meaning thicker, it will separate those light frequencies out. We get a bending effect. With radio waves, we've got a radio wave impinging upon a change in the ionosphere, which causes the bending. You might be wondering, well, what's changing in the ionosphere to change its density? Well, the higher you go, the closer you get to the sun, the more ionization occurs. So we have a much more ionization up here, less and less and less coming down. It's those changes in electron density in the ionosphere that actually cause this refraction effect. We're going to get into a few more specifics here. I'll mention some of them here. There's two terms, critical angle and critical frequency, that are coming up. We're transmitting from here, and the critical angle is the highest frequency that you can send that will refract enough to come back down to the Earth.
The highest angle.
Highest angle, yes, that will come down. Thank you, Gary. If the frequency is too high, there won't be enough bending in the ionosphere, and there will be some refraction occurring here, but the wave will pass right off into space. Real important for us. So this is probably obvious from the previous discussion, but the ability of the ionosphere to bend or refract radio waves depends upon how strongly the region's gases are ionized and the radio frequency, because there would be a lot more free electrons up there with greater ionization, and that's what interacts with the radio waves. The stronger the ionization, the greater the bending. That's why we love sunspots, but that's in the next section. The higher the frequency of the wave, the less it is refracted. Remember the previous one, we saw that signals were actually going off into space. The higher the frequency of the wave, the less it is refracted. VHF and UHF are hardly refracted at all. That's why we never talked about long distance skip on 2 meters and above. There are some weird effects that can happen there, but we won't be getting into those. Now here's the two terms that can be very confusing. Talk about critical angle, and this is the way it appears in the pool. The highest, and when you see this in the test question, you're going to want to pick lowest, okay? I'm just warning you. That's why I italicize this. The critical angle is the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions. So you can see this takeoff angle is steeper than these. So that's why it's the highest takeoff angle. And then the other term that we'll see, this is a little bit harder to visualize, but critical frequency at a given incidence angle, which in the context of what I'm going to talk about is basically straight up. It's the highest frequency which is refracted back to Earth. So if we were to shoot a signal straight up and then watch what happens, this is something called an ionogram. What it is a swept radar where signals are being shot straight up into the air. Dave Kassler had a real interesting description of this where he showed where the sweeping frequency actually appeared on a ham band. Well, what happens is they'll shoot a signal straight up and then see what comes back down again. They'll raise the frequency, so we're gone from 2 to 2.5 megahertz, raise the frequency, ping it again, see what comes down. And by this process of sweeping the frequency and watching for the return echoes, they can actually determine where the E, F2, and where these other layers appear. The reason that we've got red and green in here, there's another really weird effect in the ionosphere. When you shoot a signal into the ionosphere, it breaks into two elements called the ordinary wave and extraordinary wave. That's what the what this represents, the different colors. A lot more on that in the extra class. But what I wanted to illustrate here was critical angle, highest takeoff angle that will return a radio wave to Earth. And we saw that here. Highest angle that will return a radio wave to Earth. And then the critical frequency, the highest frequency which is refracted back to Earth. So be careful not to get those confused. Critical angle is really what affects us most in terms of long distance communications. Now remember I said that refraction is a result of changes in direction as a result of the density of the medium changing? Well, here's a little picture that this shows the electron density. So we start off down here, and as we increase in height, the density becomes greater than greater. This is free electrons per cubic meter. So more and more and more between the D, the E, and the F. And these sudden changes in density, and gradual changes for that matter, are what causes the density that creates the refraction. So there's a night density curve and a daytime density curve here. Now the way that this is measured, a little bit more on critical frequency, this is a more technical diagram of an ionogram. Not something that appears in the pool, but it's just absolutely fascinating. As they use this swept radar to shoot straight up, we get these effects, the E and F going on, and this much lighter trace is double the height of the first one. What's happening is signals are going up and being returned from the E and F layers, coming down to Earth, bouncing back up again, and appearing. So this is actually a ghost image from this swept transmitter. So here we see the frequencies, the electron density curves, and there's several resources. These links will all work for you if you care to research it a little bit further. Dave Kassler has a entire video on ionosones and ionograms, the YouTube, and a few more things here. The location index gives these values for a number of places around the world. Again, that's just supplemental information, but I found it fascinating, wanted to share it. So let's focus in on another concept here. Remember we talked about skywave, space wave, and ground wave? Well, space wave is signals that go up into the ionosphere, and then if the frequencies and the incident angles are correct, they'll come down someplace else. So this is skywave. Now, the places where the skywave comes down, we're transmitting here, and we want to talk to a friend that's out here someplace. Well, that's going to work just fine. There's the ground wave that we talked about. Ground wave only goes out a little ways. Remember, the F layer could go out to 2,500 miles. Ground wave, even at very low frequencies, is only good for a couple of hundred miles. So this zone between where ground wave can't communicate, but before skywave comes down, is called the skip zone. It's normally not possible to have your signal be heard when it's between these two locations. This is called the skip zone. That's going to become important when we get to scatter communications in the third section. All right, and for me, I was going for worked all states, and I wanted to get it on multiple bands. And on 20 meters from where I live in South Carolina, it was not possible normally to get into Georgia. So Georgia was one of the last states that I got on 20 meters. But one day the conditions were just right, and I did manage to get there. But so Georgia was in the skip zone here. I couldn't talk to people in Georgia no matter what I did till the conditions were just right. And that seems kind of strange because Georgia isn't very far from South Carolina. But it was, my signals were skipping right over it. So we talked a little bit in the diagram about skywave and ground wave propagation. We talked about hop. Hop is one reflection from the ionosphere. And then skip, propagation by ionospheric refraction. The higher the reflecting region, the longer the hop. Reflecting or refracting, same idea. Now this is the distance expressed in terms of the pool question. The approximate maximum distance along the Earth's surface covered in one hop of the F2 region is 2,500 miles. So we'd need a couple hops to make it over to Europe. Another separate pool question. The F2 region is responsible for the longest distance propagation because it is the highest ionospheric region. It's like a pool table. If you shoot at a fairly shallow angle, the ball's going to go much further. Same idea. And then a third pool question. The approximate maximum distance along the Earth's surface covered by one hop of the E region is 1,200 miles. So we see the E is about half of the F in terms of maximum hop distance. And then ground wave, as we saw, is propagation along the Earth's surface. So where the ground wave propagation isn't possible beyond that limit, and we're not into the place where the signal is coming back down again, that's the skip zone we talked about. Just the same concept, but a different diagram. Trying to get this drilled in because there are some questions we'll need to know. Remember the need to know and the nice to know? The need to know was the blue text, and the nice to know was everything else. But nice to know helps you remember the need to know. That's why we try to give you a good mix. So ground wave distance is limited by ground losses. Skywave, or skip, goes up and comes down at a distance. I realize some of this is a repeat of what we talked about, but repetition is one way to get it into long-term memory. There may be a zone too far for ground wave and too close for skywave. This is called the skip zone, just saying some of these things in different ways. And there's often no communication possible in the skip zone. Just a bigger picture of it. Notice that they've labeled these things as rays here. And the diagrams that we're seeing kind of imply that the radio signals are these little skinny pencil beams, like laser beams. Actually, we're coming off our antennas at a much wider angle than that, 15, 20, 30 degrees. So when we're sending a signal up, it's actually covering a much wider range than these little pencil beams that we're seeing here. The concept of multihop is when we go from our transmitter up to, and we'll use the F layer, transmitter up to the F layer, then we come back down, and then when it hits the Earth, it can go back up again for a second hop to the ionosphere and back down. So that's the concept of multi-hop. Now, long and short path is very interesting, kind of a mind blower. We know that the circumference of the Earth is about 25,000 miles. So let's consider a signal going from Senegal, Africa to Italy. Africa to Italy. Now, the short path for that signal is between those two locations. It's about 2,400 miles. Now, what would happen if you were, let's just say you're using a beam antenna, and you pointed it 180 degrees away from the station you were wanting to talk to? Well, it's possible with multi-hop for that signal to go from the Earth to the ionosphere to the Earth and multi-hop all the way around the Earth and come back over here in Italy. That's the concept of long and short path communications. So to make a long path contact, point your antenna 180 degrees from its short path heading. Now, it is possible that the station that you're needing to call, maybe it's a DXCC entity that you need for an award, can't hear you because he's in the skip zone. But going a long path, the other way around, he might not be in the skip zone. And Gary, do you remember your story?
We'll get Bruce to turn my mic on. Yeah. I had a friend who was going on a DXpedition to Montserrat. And Greg went down there and said, hey, let's have a schedule. Call me at this time. And so I was up in Michigan at the time. And so I pointed my antenna south toward Montserrat at the time and called and called and called. And no good. So then I turned my antenna 180 degrees, going the long way around the world, and I called Victor Papa 8 Mike United, or Victor Papa 2 Mike United, whatever the call was, and Greg came right back to me. So sometimes to get there, you have to go the long way around the world. And as I have the microphone right now, as an aside, during the CQ Worldwide Single Sideband Contest this weekend, who was my last contact? K8GL, my friend Greg, who's now back up in Michigan. So that's my long path story.
All right, very good. So that really happens. And sometimes, especially, and I realize that most of the people, you're just at this point wanting to upgrade to a general, so you're probably not huge DXers yet, but you probably will be. So at some point in the future, there's 340 countries or entities, as they're called. And when you start getting into the higher numbers, it gets harder and harder to get what's called an ATNO, or an all-time new one, and you'll want to pull every trick out of your hat that you can to try to get those. All right, well, we'll continue. So we were talking about long path and short path, and the reason that would work is that in one of the paths it'd be in the skip zone, the other path it may not. And it may be possible to have a long path have the propagation when there's nothing available via short. Generally speaking, short path is what the vast majority of your contacts are going to be, because it takes a lot more energy. There's more attenuation when you go around the other way. A few more notes, long path and short path, and then we'll get into some questions. So most HF contacts are made via short path, which is the most direct route. Long path, we know about that. We know to make a long path contact, you point your antenna 180 degrees from the short path heading. Be a little hard to do with a dipole, unless you were very patient and had a lot of trees, but beams. A signal may arrive, okay, this is kind of interesting. A signal may arrive via both long path and short path propagation, resulting in a slightly delayed echo. I've never observed this myself, but let's say that you were operating CW and you did a single dot, and then maybe a seventh of a second later you'd hear that echoed back to you. That would be pretty interesting. Have you ever seen that, Gary, or heard it?
Yeah, I heard it in the contest this weekend, actually.
Really? Wow.
Certain stations.
Okay. So occasionally you can hear your own signal coming all the way around the world. It takes about a seventh of a second to make it there. All right. So I'm sure everybody memorized the blue text as it was going by. We'll get into some questions. Which ionospheric region is closest to the surface of the Earth?
Alpha.
Alpha, the D region, yep. What is the approximate maximum distance along the Earth's surface normally covered in one hop using the F2 region?
Charlie.
That's Charlie. Yep. The F2 region is the highest, so that's why it comes down 2,500 miles, and the E comes down much less. And speaking of the E, that was the next question. All right, distance along the Earth's surface, one hop in
Bravo.
the E region,
Bravo.
right? Yep, kind of gave that one away.
Bravo.
Bravo, correct. And then why is skip propagation via the F2 region longer than that of the other ionospheric regions?
Charlie.
It's the highest, yes, the pool table image. What does the term critical angle mean as applied to radio wave propagation?
Delta.
Delta.
Yep, highest, and thank you for getting the highest takeoff angle. In the past, everybody was going for lowest, but I changed the way that I presented it, and you got it. What is meant by the critical frequency at a given incidence angle?
Alpha.
You said alpha, right?
Yep.
Okay, the highest frequency which is refracted back to Earth. Yep. So we've got critical angle and critical frequency. If you get those confused, you might want to review them. Why is long distance communication on 40C and 160 more difficult during the day?
Charlie.
Charlie, the D region absorbs signals at these frequencies during daylight hours. Which ionospheric region is the most absorbent of signals below 10 megahertz during daylight?
Delta.
That's the D region,
Delta.
or destructive region. How is a directional antenna pointed when making a long path contact with another station?
Charlie.
Yep, 180 degrees opposite. What is a characteristic of skywave signals arriving at your location by both short path and long path propagation?
Delta.
Yes, you might hear a slightly delayed echo. And some of these distractor answers are actually kind of hilarious. All right, from there we'll move into the sun. 8.2.
That's going to hurt.
Yeah, it could hurt. You better put your sunglasses on for this part of the presentation. as long as you can still see. So sunspots in the solar cycle, approximately an 11-year cycle. And for HF people, this is ultra important because we're just coming out of solar cycle 24. We're entering into 25 and propagation is improving. So during those couple of years between peaks of the solar cycle, hams get very grumpy because there's not good propagation. Now the sunspot number, this is actually the universities and scientists point telescopes at the sun. Don't dare do this with the naked eye, and count the dark spots on the sun. Those are spots where increased radiation is coming through. They're not really darker, they just appear that way because of what's surrounding them. So the sunspot number represents the number of sunspots present at a given time, and that would be facing the Earth. Sunspot numbers are useful in assessing overall solar activity. So a lot of stuff comes from them. The more sunspots, the more UV is generated. For propagation, that's a good thing. And the pool question, higher sunspot numbers generally indicate a greater probability of good propagation at higher frequencies. So over the past couple years, 10 meters, 12 meters, 15 meters have been just dismal. They're really getting hot now and improving. So here's some pictures. This is during active sun. It's a little hard to see here, but there's little dots all over. And during solar minimum, there's hardly any at all. There was a time a year or so ago where the sunspot number was hanging out at 0 for days in a row. Very sad. So during low periods of solar activity, these are the higher frequency bands, 15, 12, 10 meter bands are the least reliable for long distance communication. So low solar activity, the upper bands can be completely dead. Here's another picture of the way it works. The text is too small to read, but these peaks are occurring at about 11-year cycles. So we have a peak and then a dismal valley, peak, valley, and so forth. And then there's some notes here on when you can try operating during the day and during the night at different on different bands. I won't go through that. Solar activity is one band that's fairly magic. The 20-meter band usually supports worldwide propagation during the daylight hours at any point in the solar cycle. So 20 meters was our friend during that minimum solar activity. Another question. Rotation of the sun's surface layers around its axis on a 26 to 28-day cycle causes HF propagation to vary periodically. And Kessler's comment on this was pretty interesting. It kind of defies logic that the equator is actually moving faster than the poles on the sun. So it causes this variation in rotation. Big ball of squishy gas, I think is what he called it. In summertime, on the lower bands is not always our friend. We talked about the D layer not being our friend because it was absorbing the lower frequencies. Now in summer, the conditions are just perfect between humidity and temperature to cause thunderstorms. So lower frequencies typically experience high levels of atmospheric noise or static. And you can definitely hear this. Now there's a couple of solar parameters that we'll talk about here. We'll get into many more when we get to the extra class in January for those of you that will be joining us. So SFI is the first one, Solar Flux Index, measure of solar radiation at 10.7 centimeters wavelength, which is 2800 megahertz. And this number, the SFI number, correlates directly to sunspots. In fact, the SFI starts out at 65 and then goes up linearly with the sunspots. And then we have the K index and the A index. And I wish they would have named these the other way because I think of things alphabetically. But the K index is the short-term stability of the Earth's magnetic field. This is a measurement that's made at points all around the world. Every 3 hours, they will generate a number. 0 is quiet, 9 is an extreme storm. So this is the short-term stability. So if you're interested in good propagation, you'll generally want to see the K index in particular to be fairly low, 0 or 1. The A index is the long-term geomagnetic field stability. And the way that works is they take 8 values. Remember, they were 3 hours for the K index. They'll take 8 of those values, which covers 24 hours, and create what's called an A index. You can kind of see it averaged over time. Now, I've seen quite often where the A index is relatively high compared to the K index. The K is the only one I really care about because that's what the propagation is doing right now. Here's an example of index over time. So if you can associate the letter A with average, that may help you, average being averaged over 8K periods. And we're into some questions. We're moving right along. How does the higher sunspot number affect HF propagation?
Alpha.
Higher sunspot numbers generally indicate a greater probability of good propagation at higher frequencies. Exactly. Which of the following are least reliable for long-distance communications during periods of low solar activity?
Delta.
Delta.
Yep, the high bands kind of go away on us. 15, 12, 10 meters don't work so well. At what point in the solar cycle does the 20-meter band usually support worldwide propagation during daytime hours?
Delta. Yay.
At any point. So that's a band that you're going to like. What causes HF propagation conditions to vary periodically in a 26 to 28-day cycle?
Charlie.
Charlie.
Sun's rotation on its axis. Correct. Which of the following is typical of the lower HF frequencies during the summer?
Delta.
High levels of atmospheric noise or static. Yes, and those lightning strikes can go for hundreds of miles, so it kind of raises the noise level on the entire band, even if the storm is nowhere near you. So what is the solar flux index?
Delta.
Measure of solar radiation with a wavelength of 10.7 centimeters. And I don't know if it occurred to anybody, why would you want an SFI index and a sunspot number index since they're both related to each other? And the only answer I could think of was that you can measure the signal levels at 10.7 centimeters during the day and during the night and when it's cloudy. So it kind of gives you a reference when you can't see the sun. What does the K index measure?
Bravo.
Bravo.
It's the short-term stability. So if you're in the process of, you're going to start a contest or you're trying to work a DX station, you want a fairly low K index. The A might be high, but you don't care. You're really concerned about what it is right now, which is the K.
And note there was the Earth's magnetic index, not the sun, which is a distractor. See that
okay.
down below?
Yep. Things that you could trip on. Yes. Yep. It's good to note those so you don't trip. Okay. What does the A index measure?
Charlie.
Charlie.
Charlie. Long-term stability of Earth's geomagnetic field. A and average might help you. And then we've got a few more things to talk about in assessing propagation. MUF and LUF. I think I've reworked this to the point where I hope it makes some sense. This is an area that's confused students in the past, but we have such a great group here. None of you are going to be confused. MUF, maximum usable frequency. There'll be a question that asks, what is MUF? Maximum usable frequency. Frequencies higher than that aren't going to work. Maximum usable frequency, and this is a pool question words, maximum usable frequency for communication between 2 points. Frequencies higher than the MUF will not be refracted enough to get bent back to Earth, so they just get lost in space. LUF is the other big concept. That's the lowest usable frequency. Lowest usable frequency for communication between 2 specific points. So if you go any lower than that, it won't get through. Frequencies lower than the LUF will be attenuated before reaching the destination, or completely wiped out. So take a minute to think about that. MUF, maximum usable. LUF, lowest usable frequency. Frequencies lower than LUF will be attenuated or be completely absorbed. And this is the Goldilocks area. Not too hot, not too cold, just right. Frequencies below the maximum usable frequency and above the lowest usable frequency are refracted back to Earth. That's happiness. And here's some examples. Now let's say that the maximum usable frequency is 10 megahertz. So what would happen if we were transmitting on 10 megahertz? Well, it would refract, but just barely, because that's the edge. The maximum usable frequency is 10, so it'll refract, but just barely. So it's much better to be a little lower than the MUF, or one band below whatever the MUF is. Now, the MUF is 10 megahertz. What if we were allowed to transmit on 12 megahertz, which we're not, but that's above the MUF? This signal will pass into space, will not return to Earth. You notice the sad face. Well, the MUF again is at 10 megahertz in this example. We're going to try transmitting at 8 megahertz, which you better not, because we don't have a ham band there, but this is just an example. Okay, 8 megahertz is below the MUF, and this will refract back to Earth. And that's a happy face. So the rule of thumb is whatever the MUF is, you pick the next lowest band without being over the MUF, of course. So that's MUF examples. Now, lowest usable frequency examples, let's say that the lowest usable frequency is 5 megahertz. So if you transmitted at 5 megahertz, that's 60 meters, refracts, but just barely. So you need to be a little bit higher than that. So the lowest usable frequency is 5. Here we're going to have something that's below the lowest usable frequency at 4. It's below the LUF, gets absorbed by the ionosphere, will not return to Earth. Sad face. At 6 megahertz, that's above the lowest usable frequency, so that will refract back. So you have to kind of think through some of these because the pool questions will, if you can't remember exactly what LUF and MUF are, it'll be hard to get those right. I've got some diagrams coming up that I think are helpful. So here we've got the maximum usable frequency, and where we want the optimum, well, if we want to have good communications, we want to be a little bit below the maximum usable frequency. They call it the optimal working frequency here, a little bit below the MUF. And of course, they have to be above the LUF, lowest usable frequency. So it's got to be in this band. The temperature of Goldilocks' porridge. Now here's a really weird thing. This actually can happen. So what if the LUF, lowest usable frequency, is above the MUF, maximum usable frequency? Well, guess what? There's going to be no communication possible. That's a radio blackout. And this can happen as a result of a solar flare. Solar flare? How about a solar flare? I like to make up words. So assessing propagation, okay, factors that affect the MUF, path, distance, and location. Remember we saw that on a map of the Earth, and signals bouncing around, the time of day and season, time of day, how much ionization is there in the atmosphere, solar radiation in ionospheric disturbances. And this feels strangely like an all of these question coming our way. All affect the MUF. And this is something we've said already, but this is in terms of the pool. The frequency that will have the least attenuation for long-distance skip propagation is just below the MUF. Remember this diagram that we saw. So if the MUF is 15, pick the next lowest band, or 20 meters, which would be 14 megahertz, and that should be a good band for long-range propagation. And remember, we said if LUF exceeds MUF, propagation via ordinary skywave communication is not possible over the path. That would be a radio blackout. It's a fairly rare condition, but it absolutely does happen. And then they've added this question, or changed it in this pool. I like what they did in the change. It says, to determine the current propagation on a desired band from your station, use a network of automated receiving stations on the internet to see where your transmissions are being received. Well, let's put that in some practical terms. There's something called the reverse beacon network. What the reverse beacon network is, it's stations all over the world that are listening to CW and PSK 31 and FT8 signals, and they will report the signal strength from any of those modes onto a database. So you can operate CW for an hour, let's say, like during a 1-hour contest, and then when you're done, go over to the reverse beacon network and see where you were heard any place in the world. Or if you're not wanting to learn CW and dedicate an hour to it, you can actually program like 3 V's, for example, which is kind of a standard test signal, then the word test, and then your call sign. The reverse beacon network will pick up that sequence, the same as a CQ call sign, and report. So you could be sending those test signals for a couple minutes, and then let's say you switch to a different antenna, send the same test signals, check the reverse beacon network and see which of your antennas was working better. That's a practical example. To determine current propagation desired band from your station, use a network of automated receiving stations. I just gave you an example of the reverse beacon network. We talked about WSPR, WSPR, the low level propagation reporting mode. That's another means that you can use. And you can also listen on a remote SDR, like websdr.org is a site that you can go to that will have SDR receivers. They're spread around the world. So you can be sending a test signal and then listen to yourself at that remote site using this facility. So those are examples of the way that you can do that. Another method is there's something called the Northern California DX Foundation, and they have a series, or coordinated series of beacon stations that are transmitting all the time. You can tune in and see if you can hear them. If you can, then propagation is open. So again, be sure to catch the need to knows here. The beacons, so what we talked about just now. And this is just a piece of general information. If you're seeing skip on 10 meters, long distance on 10 meters, it might be a good indicator that 6 meters might be open as well. A lot of people never check 6 meters because it's closed so much at the time, but when things are really booming on 10, it's worth a look. There's a couple of propagation prediction software programs. They're free. VOACAP is one. I think Gary wrote that, didn't you?
Yeah.
No, that's the Voice of America. Your taxpayer dollars paid for this, and it's pretty fabulous. I think we'll have time. We'll have a demo of that coming up a little later. Prop is another one. And these are both links. So when you get the PDF, you can go to those sites. How else can you assess skywave propagation? Well, you can call CQ on a dead band. It's amazing, even though you don't see any signals, if you call CQ, you might get somebody from Southern Africa returning your call. Sometimes a band is dead just because nobody's using it, nobody's trying it. And FT8 decodes are fabulous because if there's any activity at all going on, somebody's going to be on FT8. And I've listed the FT8 frequencies here. I've got these programmed into memories on my transceiver, and I can just quickly, by turning my memory button control, I can scan through all of these frequencies in a matter of seconds. And I can immediately tell if there's anything going on these bands. If you have the ability to decode FT8, you can see where they're coming from. So you could see if propagation is open to Europe on 20 meters, for example. Even if you're not interested in operating FT8, to know that that band is open, that would encourage you to try it on CW or sideband. So a little bit more here. Actually, what I'd like to do at this point, because it's 7:26, let's go ahead and take our break at this point, and then we'll get the second half of this section right after the break. We'll kind of break it up in the middle. So we'll take a 5-minute break at this point. So stretch, pet your dog, or let your cat outside, or whatever you want to do. We'll be back in 5. we're going to pick up on the rest of section 8.2. They nicely divided it into two pieces for us in the book, and that's the way that we're approaching it here as well. So a little bit more on ultraviolet, X-ray, and solar particles. We're going to be talking about the speed of light and the speed of particles. And if you can get that concept when we go through it, that'll help you with a number of the pool questions. So we know that ionization is a good thing. Here's the sun shining down toward the Earth. The Earth is facing the sun here. So ionization is a good thing unless there's too much of it. So there's too much of it that can happen during a solar flare or something called a coronal mass ejection and magnetic storm. And these high levels of ionization can actually cause radio blackout. So the right amount of ionization is what we're looking for. And we're not very excited about disturbances that are going to hurt propagation. I looked and looked, and I finally found a picture of a disturbed ostrich. That's what this is. So there's several kinds of disturbances. Now remember, disturbances, with one exception, we'll get to a little later, disturbances of any kind are a bad thing, and they're going to have a negative effect on HF propagation. And that little fact will help you with several pool questions. So what are some of these disturbances? We've got a solar flare. This is a large eruption of X-ray and UV energy and solar material on the surface of the sun. And because this is light, X-ray and UV, that's coming at us at the speed of light. And you may remember from your science class that it takes about 8 minutes for the light to go from the sun to the Earth. There's no warning for these. We can tell when certain things are coming are coming around the sun and facing the Earth, but these generally aren't predictable. Then we've got a coronal hole. It's a weak area in the sun's outer layer where ionized gas and charged particles escape the sun's magnetic field. Okay, charged particles. Particles move at the speed of particles. So we've got the speed of light, we've got the speed of particles. You're probably saying, Dave, what's all of this about? A CME, coronal mass ejection of large amounts of material, I think Hassler called it junk, ejection of large amounts of material from the corona, and that's coming at us at the speed of particles. All of these disturb HF communication. So if we see these in a question, we'll know that they're bad, with one exception coming up. So we got a light bulb. UV and X-ray radiation from a solar flare affects radio propagation on Earth in approximately 8 minutes. That's what I mean by the speed of light. X-ray and UV, typically from a solar flare. Solar flare is also called a sudden ionospheric disturbance, or SID, and increases in D region ionization and absorption increase dramatically and can cause a radio blackout. So too much ionization is a bad thing. So an SID, sudden ionospheric disturbance, affects the lower frequencies more than the higher frequencies. So if it's going to wipe out something, it's probably going to be 40 meters and below. And it kind of makes sense here, but a sudden ionospheric disturbance only impacts the sunny side of the Earth. It's the only side of the Earth that can really sense it. So daytime, nighttime effect. Now we're going to talk about geomagnetic disturbances. These are from result of charged particles coming off the sun through one of the other kinds of disturbances. So the particles that are given off from the sun are called the solar wind. There's actually a parameter that scientists measure for that. So sun gives off a stream of particles called the solar wind. Coronal mass injections, or CMEs, take 15 hours to several days to reach the Earth. Now this is the speed of particles that I was talking about. So that affects coronal mass injections and coronal holes. Blue text. Particles increase ionization in the E region, and cause auroral displays in geomagnetic storms. Now, you've probably all seen or heard of the northern lights, beautiful colors in the northern sky at night. That's caused by the same effect, particles coming in from the sun. Yeah, they tend to be attracted to the poles, the North Pole and the South Pole of the Earth. That's why they're typically only seen at higher latitudes. Now, it's not the light that affects us in radio land. It's the electrical charges that are associated. So some people get that confused. So the aurora that we see can be a beautiful light show. It also affects propagation, but not because of the light. So here's a couple of examples. Solar flare. Looks like the sun is having a baby. A large coronal hole in a CME, coronal mass injection. So a flare again emits light, X-ray and UV, coronal hole and CME particles. And here's a lot more information here at this link. Geomagnetic disturbances. Geomagnetic storm is a temporary disturbance in the Earth's geomagnetic field. And because it's from particles, it can last from anywhere from hours to days. And it degrades high latitude HF propagation. Geomagnetic. Propagation may be wiped out for a period of hours to days. And here's a picture of the Earth with a bar magnet in the middle, and those charged particles tend to come in at the poles. A little bit more. Now, auroras are a glow of gases ionized by the incoming charged particles. And some of that shows up as light, some of it shows up as just charged particles, which affect radio, electromagnetic waves. They flow into the atmosphere, guided by the Earth's magnetic field. Now, here's the one exception where all of these bad things I've talked about can be a good thing. A benefit of geomagnetic activity creates auroras that can reflect VHF signals. This is typically propagation that happens over the Earth's poles. So that's if we're seeing an aurora, visible aurora, there's probably an electrical aurora that will improve VHF propagation. Strongest on 6 and 2 meters, and because of the nature of what's going on, it has a hissing or buzzing sound. And on it is some questions. All right, let's see if we can remember LUF and MUF. What does LUF stand for?
Alpha.
Alpha, the lowest usable frequency for communication between two specific points. What does MUF stand for?
Bravo.
Bravo.
Bravo, the maximum usable frequency. What factor or factors affect the MUF?
Delta.
That's all of these choices, correct? Time of day, distance, location, radiation. What usually happens to radio waves with frequencies below the LUF?
Charlie.
Charlie, attenuated before reaching the Earth, reaching the destination. Generally speaking, that just means they're completely absorbed. It's maximum attenuation would be zero signal, of course. How does the ionosphere affect radio waves with frequencies below the MUF and above the LUF? You think about this a little bit once.
Alpha.
Alpha.
Yep,
Alpha.
that's the happy region, reflected back to Earth. What happens to HF propagation when LUF exceeds the MUF?
Alpha.
Alpha.
Propagation via
Yes.
ordinary skywave communications is not possible over that path. That'd be a radio blackout. You folks did great with that. Which frequency will have the least attenuation for long distance skip propagation?
Alpha.
Alpha.
Alpha, just below the MUF. Which of the following is a way to determine current propagation on a desired band from your location?
Alpha.
Alpha is correct.
Alpha.
Use a network of automated receiving stations on the internet to see where your transmissions are being received. And we gave some practical examples of that. Approximately how long does it take the increased ultraviolet and X-ray radiation from a solar flare to affect radio propagation on Earth?
Charlie.
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 Speed of light. I was pressing the shift key and couldn't figure out why nothing was happening. What effect does a sudden ionospheric disturbance have on the daytime ionospheric propagation? We know it's something.
Alpha.
Delta.
We know it's something bad, right? Because
Ah.
any of these disturbances are bad. That's why I wanted you to remember all of these things will give you an answer that's bad. And that's okay. That might have helped with that one. How long does it take a coronal mass ejection to affect radio propagation on the Earth?
Delta.
Delta.
Yep, that's particles. What is a geomagnetic storm?
Delta.
Delta. Yes.
Delta.
How does a geomagnetic storm affect HF radio propagation? We know it's going to degrade
Delta.
something for sure, and delta is
Delta.
correct. Degrade high latitude HF propagation. How is long distance radio communication usually affected by the charged particles that reach Earth from solar coronal holes?
Bravo.
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 Yep, something is disturbed, and in this case, we said HF was affected more. How can high geomagnetic activity benefit radio communications? That was our one exception.
Alpha.
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 Create auroras
Alpha.
that can reflect VHF signals. All right, now we're going to talk about scatter modes. There's not a lot here, but it's interesting. And then after that, I've got 3 or 4 little sections of supplemental material that will be extremely helpful in your ham radio career, but they're not really related to answering the test questions. So I hope you'll be interested in hanging around for that. Okay, scatter modes. Ionospheric reflections. Now, there's something going on here. Let's see. Something going on here. Remember I said that these nice, even regions didn't represent reality? Well, they're actually not that even. They're kind of jagged and they're changing all the time. So what can happen is that radio signals can go up into, in this case, the E region, and because of discontinuities and differences in the electron density profile, all of the signal isn't necessarily going to go up here. Some of it's going to get scattered. Now, remember the skip zone we talked about? When we get past ground wave propagation, and we're earlier than skip, we're in the skip zone where you normally can't hear anything. So this is a bit of an exception here. Ionospheric reflections that occur that don't go all the way up to the main layer that they're aiming for and coming back down will scatter some RF back down again that will actually land in the skip zone. So this type of propagation will fill in some of those dead spots. So we've got it happening here at the E layer and the F1 layer, up and back down. So this is called scatter. When you can communicate, this is called scatter communications. It's unpredictable. You don't know when it's going to happen, but thank your lucky stars when it does. That's probably how I got Georgia. So another effect that happens when the signal, the main signal I'm calling it, comes down, it's going to bounce back up. Remember the multihop we talked about? Well, it's going to go in different directions, most likely, and some of it will actually scatter back into the skip zone. That's called backscatter. So it's a way to get radio signals into the skip zone that normally you'd never be able to hear. So these are called scatter modes. So scatter propagation allows signals to be heard in the transmitting station's skip zone, too far away to be received via ground wave, but too near for skip. So that's one characteristic. And scatter coming from the forward direction is just called scatter. If it's being bounced up from the ground at the destination, that's backscatter. The effect is the same. So this is a little bit more realistic view of what the ionosphere may look like. This might be kind of hard to read, but what the words say is reflected rays scatter in all directions. So we've got something coming up here, and due to odd discontinuities in the ionosphere, they might come down here, they might come down there. Here's one that's coming from way over here and coming back. So because the main amount of your skip or your transmitted signal is going to go up to the E or F layer and come back down again, a little bit of it might get scattered as it's going through these discontinuities in the ionosphere. So because of that, there's not nearly as much RF, so signals tend to be weak. Only a small part of the signal energy is scattered into the skip zone. So one characteristic is that they're weak. All right, here's another characteristic. Remember when I said when you get a whole bunch of things together, it's usually in all of the above or all of these? Well, this one isn't. These are actually all separate pool questions. So here's the second characteristic of scatter. Signals typically have a fluttering sound, and that's because of basically a multipath effect. They're coming from all different angles, sometimes canceling out or reinforcing. That causes the fluttering sound. And they often sound distorted. Energy is scattered into the skip zone through several different paths, which again is multipath, like this one. So those are three separate pool questions. And then we're going to talk about near vertical incidence skywave. Some people call that, it's NVIS, or some people call it NIVIS. Whatever you want to call it, it's short distance, medium frequency, or high frequency propagation using high elevation angles. And the basic idea, I think I got a bigger picture here. Here it is, yeah. The basic idea is that we're shooting a signal almost straight up into the air. And this can be very helpful in a mountainous region. In the place where Dave Kessler lives, they've got a lot of mountains, and they run some of their HF nets using NVIS. It's the only way that they can, for example, here's a transmitter. Well, this mountain peak is blocking this signal, but if we go up and down, we can get into the valleys. So it's something that hams use in mountainous areas. The military uses this. So here we're transmitting. It's obvious that we're going to have to be using a frequency that's below the critical frequency here. So we're shooting almost straight up. We want it to come down and not go off into space. So 50 kilometers isn't too terribly far. I don't know what that is in miles, but let's call it 50. So that's a picture. So reflections from a signal using high elevation angles are scattered back to Earth over a short range around the transmitting station. I showed you the bigger picture. And the most effective antenna would be a low dipole. Now normally if you put up a dipole, you want it to be at least half a wavelength above ground so that you'll get some directional properties. But folks that are doing NIVIS on purpose will make that much lower, like an eighth to a quarter wavelength high. Omnidirectional pattern, very high angles, works best at 40 meters and lower frequencies. So some people call this a sky warmer or a cloud warmer antenna, because you're going up and it's coming back down, but because of the effect there, they call it sky warmer or warmer antennas. But you get this reflection effect close in. And there's our larger picture. In this case, the reference is the F layer due to the frequency that's being used. And then right into some questions. So, yeah, go ahead.
50 kilometers is 31 miles.
Okay, thank you, thank you. I would have done that conversion, but I didn't think of it. So it's relatively close in because 30 miles is within ground wave distance on the lower bands, and it's way closer than skip distances on E and F. All right, what type of propagation allows signals to be heard in the transmitting station's skip zone?
Bravo.
That's scatter, correct. What is a characteristic of HF scatter?
Bravo.
Bravo again.
A fluttering sound. Yep. What makes HF scatter signals often sound distorted?
Delta.
Delta.
Yep. Energy is scattered into the skip zone through several different paths, distorting the signal. Why are HF scatter signals in the skip zone usually weak?
Alpha.
Correct. Only a small part of the signal energy is scattered into the skip zone. What is near vertical incident skywave propagation?
Bravo.
Bravo.
Short distance MF or HF propagation at high elevation angles. And that concludes the theory and the questions. I've got some supplemental material now that I think you're going to find very interesting. First of all, there's two books. If you want to learn more about propagation, you might not want to learn a lot more right now because you're going to be a new general, or at least most of you. But as you get into chasing DX and awards, some of this information you're going to say, oh, what was it we talked about there? Well, here's two wonderful books. The first one, Understanding Ham Radio Propagation. This was our friend Michael Burnett that we had commented on before in our Learning How to Learn session. I got to attend his propagation talk at Hamvention this year in June or whenever it was. He's just a very entertaining speaker, and he writes very much like he talks. So I found this book a lot of fun to read. Gets into some of the technical aspects. This book just came out from the ARRL, probably within the last 2 months, and it's a little bit more technical, but it also is excellent. So I'd highly recommend either one of these. I think they're both available as Kindle books, and well, I know that this one is, and is print. Usually Amazon is a little cheaper, especially if you're a Prime member, because you can get free shipping. So some books that I'd recommend if you care to go further. You may in the future. The next one, you've probably, if you've gone to QRZ.com and as an HF operator, you'll probably be doing that a lot because most hams will put their biographical information on QRZ. So people are going there all the time. This is one of the standard panels that shows up when you first open QRZ. And this panel of propagation information is published by Paul Herman, N0NBH. And he's got a ton of stuff in addition to this little panel. He offers for free people to use his code and put them on their QRZ page or any kind of a ham radio page. So you'll see this all over the place. It's extremely useful. I think I can, wait a minute, I have to turn this off. All right, just give you a quick peek at, there we go. Are we displaying that?
Yes.
All right. Yep, there's all kinds of information that he's got here, including the same band information. And I really like this because some of the things we've talked about, and this is from today, 31 October 2023. This gets automatically updated about once an hour. the sunspot number, 116. I look at this, I call it a propagation panel, just about every time I turn on my radio because I'd like to know what's going on out there, want to know if there's any chance that I'm going to have good propagation and what to expect before one of the 1-hour CW contests that I like to do or any kind of fooling around. I just like looking at this. So sunspot numbers in triple digits, that's a good thing. For several years, it wasn't unusual to see this 0 for days and days in a row. So here's SFI. These correlate. The A index and the K index. Because I've been watching this a lot, I'm starting to see patterns. Now, I would think that with a relatively high number of 9 for the A index, I'd think, well, that's pretty bad. Probably going to be disturbed communications. But the short term K at 1, that's the only one I care about because that's what's going on right now. X-ray number that we haven't talked about, proton flux, electron flux, aurora, all this, a lot of this we haven't talked about. Down here, I found this to be pretty accurate. HF conditions by band. So during the day, right now he's saying that 17 to 15 meters, it's not really him, this is a compilation of data from all over the world where it's reported from. So here we are at night. We've got all of these bands are good. And I've generally found this to be accurate. So I typically will look at the sunspot number and the band conditions. I don't do much VHF, so I don't really care if they're closed. Solar flare probability, 64%, interesting. And they show, okay, the geomagnetic field, very quiet. So that's good. And then noise level, and a current picture of the sun. But just about every time I turn on my radio, I look at this, and I've found it to correlate. It's been very helpful. So I'm going to go back to the presentation, if I can get my mouse over there. Here it is. Okay, there we go. So we just went to his site. There's 2 resources here, Understanding Current Conditions. We've got all of these funny numbers over here. Well, what do they mean and how do you interpret them? He put together a real nice diagram, Understanding Current Conditions. There's a PDF for that, and I'm going to be including that in our handouts for this class. I had intended to actually email them to everybody, but you can get them just as easily from Gary's handout link that he'll be sending out tomorrow. And then he's got a glossary. So he'll be talking about how these different factors affect propagation. Then the glossary gives you some information about what each of these funny things are, like what is BZ, for example. That's in the glossary. If you want to get to this quickly, you can, I bookmark his site on my browser, so that's typically how I get to it. If you are a frequent QRZ.com user, it's a panel that shows up there. There was a ham VE2XIP that was very baffled by this, because if this is all you see, it's kind of mind-boggling. What does all of this stuff mean? Well, his intent was to learn it, understand it, and then explain it to other people. And he wrote about a 4 or 5 page article. So this, and this are going to be in the handouts folder tomorrow. In NOAA, National Oceanic Atmospheric Association, I think it stands for. Administration, yep. Got a ton of information there as well. So, and these 3 handouts are something that I keep in my, I know when we first began this class series, I recommended that everybody have a manila folder or a binder or something where you can put information that you're probably going to be using all the time. And these 3 resources I'd certainly recommend. And those will be in the handouts folder tomorrow. And then I promised I'd tell you how I was going to get to Alaska. All right, so I'd like to be able to say that I've worked a park in the Parks on the Air program. I'd like to say that I've been able to do that in all 50 states. That's not what I wanted. There we go. That back to. And I don't have Alaska currently. I'm also missing, in chasing the Worked All States Award, Alaska is the only state that I don't have. So I'd kind of like some help in figuring out how I could maybe knock both of these off at the same time. In your case, most of our students aren't going to be interested in doing CW in the near term. Maybe sometime down the road you'd like to do that. But this is as useful for sideband or digital FT8 as well, the tricks that I'm going to show you here. So the first thing I wanted to know was, where are the parks in Alaska? Well, POTA has got a resource that I'll click on here. Try to turn this off. Yep, here it is, and I can put in a DX entity. Now, we talked about entities and states. Alaska and Hawaii are actually separate countries as far as the logbook of the world system is concerned. So Alaska, and then Alaska is within the country of Alaska, which we know is a state, is the state of Alaska. So then I'm going to kind of zoom out on this. Now, something interesting about Alaska, everybody is in the southern part of the state. And if we zoom this out just a little bit more, I don't know if you can see it, but here we've got Anchorage. So all of the parks that are in the Parks on the Air system are around this city, Anchorage. So that's the first thing I needed to know. So if I'm concerned about propagation from where I live in South Carolina to Alaska, I'm really going to be looking for Anchorage. Getting my mouse back on my screen here. So that's the first thing. Where are the parks? Well, in Alaska, they're in Anchorage. And then because we're going to be using the VOACAP software for a propagation prediction, I'm going to need to either know coordinates or grid squares. And to me, the grid squares seemed easier. There's a resource that I use frequently in identifying POTA locations called zonecheck.eu. Just give you a little picture of what that looks like. And here's the world. And if I would like to locator, that's a grid square locator, and I happen to be in EM84XX. You can also do it by address, and I could put in Anchorage, Alaska, and get the grid square for that. So what's just happened, based on my grid square, this shows, now everybody knows where I live. So I'm on Mount Zion Road. This is grid square EM84XX. And I wanted to write that down, so I'll write that down, because I'm going to need it for the propagation prediction software. And I'm going to do the same thing for Anchorage, Alaska. Turns out that Anchorage is BP51BF, and this is me. So I now have that bit of information. Now we know that propagation varies throughout the day, that more ionization, depending upon where we are relative to the sun. So also I know that people that do POTA, Parks on the Air, and SOTA, Summits on the Air, they typically have to get up in the morning and drive to whatever location it is that they're wanting to activate. So usually they're going to be out there between noon and 3 p.m. on average. So in Alaska, that turns out to be 2000 to 2300 UTC, or 4 to 7 p.m. Eastern Daylight Time. So I know what time I want to talk to them. Now the question I have is what band or what frequency will, and what band am I going to want to use to be successful in making that contact and working toward these goals of some awards that I'm chasing. So VOACAP will tell me that, and then I can go back to the POTA site. And normally when a person's going to activate a park, they'll put that park in a certain location, and it's available for others to see that they're going to be there. I'd be watching for Alaska stations in that resource. So we're going to go to VOACAP now. That stands for Voice of America.
Coverage Area Predictor.
Voice of America Coverage Area Predictor. I thought Gary might know that. Okay, now this is what will come up, and there is a means to put in a bunch of information. So what I've done, I've put in, here's antennas. I've got a hex beam antenna, which is about the same as a 2-element Yagi on 10 meters, 12, all of these bands. And then on 30 through 80, I've got the equivalent of a dipole antenna. So I put those in, and it'll automatically match the receive side to this. Well, I don't really know what the person in the park is going to be using, but that's just how the software works. So that was antennas. And then under settings, there's a whole bunch of stuff that comes up here that you can choose. I won't go into detail there, but lots of ways you can configure this. Notice up at the top, we've got select transmit QTH. You could do this by address or grid square. I did it by grid square, and I had previously looked up my grid square and the grid square for Anchorage and put it in. There's a button here that will allow you to save your settings, which isn't what I wanted to do there. Oh, I know what it did. There we go. Slow down. Okay, there we go.
Psychedelic.
Yeah, I'm making some of you people busy. Okay. All right, stop. Okay, keep my mouse from going crazy. So what I did here, I put in my location, put in Anchorage. You can put it in by latitude and longitude. You can put it in by address. So notice something interesting. I don't know why it is doing this. Notice that there's some red dotted lines on either side of my locations. Here's me in South Carolina, and here's Anchorage. What do you suppose these dots might be? Anybody? Well, that would be the long path. We can do short path or long path. Right now we're set to short path. So, but I want to know when I should try to make this contact, try to find somebody that's out there. So there's something here called the propagation wheel, which I'm going to open. And this looks kind of interesting. So red is a 100% chance of making the contact. Light blue or white is 0% chance of making the contact. Okay, so that's the first piece of information. Now notice how we've got quite a cluster of orange and red up here. And these are the bands, 10, 12 meters, 15 meters, 17, 20, 30, 40, and 80. So these are the bands, and these are the times of the day here, UTC. So 1900 UTC, 20, 2100, etc. So this area right here is when I should be trying to look for my Alaska stations. And using the interactive tool, we can see what the percentages are. If you look in the very center of the circle, you'll see 23 UT, universal time, 20 meters. I've got an 89% chance of making that contact. All right, something else over here. Stop that. Okay, I've set this to CW and 100 watts. Watch what happens. This might be discouraging to some of you, but let me switch it to single sideband. And watch the colors on the left. I don't have any oranges and reds anymore. That's how much of an advantage you have on CW.
That's why us sideband operators have to be real men.
Yeah, sideband operators have to be real men, or women. Yeah, we've got ladies with us too. So a lot of you aren't going to be interested in doing CW, at least not right away. So sideband, you look at something like this, and you'll feel really discouraged. The darkest color we've got is on the 10-meter band. And it actually shows 73%. That's better than I thought.
Oh, Dave, put it at 1,000 watts because that's what I'm operating.
Yeah, that's a good thing to do. I'm 100 watts because that's what I use. Let's put in.
What?
Is that it?
That's 1,500 or
Okay.
1,000.
Okay. I can barely see it from here. All right, notice how we got a lot more orange. So if you're running single sideband, an amplifier might be a really good thing for you. I can do most of what I want on CW and 100 watts. Now, most of you aren't going to want to do CW, like I said. You might be discouraged to see how much poorer it was on sideband. But all of you can, if you're chasing awards, all of you can do FT8. That's an easy jump for a ham. Look what happened there. That's even better than CW, significantly better than CW. So this is a really cool tool once you get to the point of chasing awards and finding out where you're going to operate. Thought you might enjoy that. And then get my mouse back over to where it wants to go. And then what I would do, the place where POTA and SOTA people pre-announce where they plan to be, I'd look there for people in Alaska during these times, and then I'd watch for them to come on the air and try to work them. So that's how I plan to get to Alaska. Alaska Parks, we showed you. How am I going to get to Alaska? We saw that. And then I drew a red circle around the optimum times for doing this. All right, mouse, here you are, okay. Turn my laser back on. Yeah, so you can see that this would be my prime times, 2100, 2200, 2300 hours, which is the UTC equivalent of local time in Alaska, giving them time to get out to the site and get on the air. So there's two flavors of propagation prediction software that are free. VOACAP we just looked at. Propy is another one. I haven't played with that, but that's also an HF propagation tool. And the idea here is that it's giving you probability, and it's taking into account all kinds of things. The sunspot numbers, SFI, geomagnetic conditions, all of that is factored in when it's making these predictions. Very cool. And then I think this,
Dave,
yeah, go
I
ahead.
got a question.
Sure.
You were back on that where you were trying to get a hold of Alaska. You pulled up FT8. It was at 1,500 watt. If you drop that wattage, would that change
Oh,
that
yes.
a lot?
Yeah, it would definitely change, and you'd be surprised to see how well you can do on FT8 even with 100 watts. So if you've got a 100-watt transceiver, which is what most generals start off with, 100 watts and FT8, if you care to operate FT8, you will work the world, quite literally. You can do it on sideband too, but you just have to be a whole lot more patient.
Right. Okay.
So I wanted to introduce you to Tamitha Skov. If you haven't heard of her before, I got to see her in person at Hamvention a couple years ago. She's usually there. She's known as the Space Weather Woman. And if you are kind of enthused, she's got a merchandise link on her website. You can order t-shirts and coffee mugs. I don't have one, but just thought you'd like to know. What I'd like to do, though, is give you an idea of what her space forecasts sound like. So we'll only take a couple minutes and just play a couple snippets from her most recent one. Her most recent one is from October 26th, just earlier. a few days ago. So I'm going to see if this will work for us. Turn that off. Click the link.
We have 2 wispy solar storms on their way to Earth, some fast solar wind, and some big flare activity maybe just around the corner. Those stories and more in the spotlight. Space weather this week kicks off into high gear. As we take a look at region 3467, it launches a wispy solar storm. You can see right here in our solar demon, all that dimming region. That is actually an Earth-directed solar storm, but it is wispy, so we're not expecting all that much. But we do have a coronal hole that you can't really see right here, but that is also giving us a little bit of fast solar wind. On top of that, if you take a look at the far shot of the sun, you can see wispy prominence eruptions. These are big solar storms that are not Earth-directed, but man, do they sure make some nice eye candy. And on top of that, as we zoom into the sun, we actually have another filament right here. This filament is about to erupt right here. You'll see it whoosh, kind of right there. Yep, that is an Earth-directed solar storm as well. It's also a wispy solar storm, so that one is going to hit us later this week. And on top of that, it's going to be chased by some fast solar wind from this coronal hole. So aurora photographers, if you're at high latitudes, you're definitely going to be getting a show over the next couple days. And the aurora photographers,
And she keeps referencing auroral photographers. Those are people taking the pictures of the light shows due to aurora.
at mid-latitudes, well, you might get a chance for a show as we move later in through the week. Now, taking a look at our solar storm conditions and aurora possibilities over the coming week, we are expecting to get that solar storm hit. Actually, we're getting it right now.
So this is a picture that will remind you of the weather forecast you see on TV. So she'll go through several contexts of this, and I'm going to fast forward to where she actually references ham radio. To me, that is a ham, by the way.
So the space weather this week is picking up. We do have a couple of wispy solar storms either hitting Earth or on their way to Earth now. Aurora photographers, if you're at high latitudes, you could get a bit of a show. Aurora photographers at mid latitudes, well, you're going to have to wait closer to Halloween in order to get a bit of a show. But it could give you some decent aurora then with some fast solar wind. As well as that, amateur radio operators, you're getting a break this week because we definitely don't have any big flare players in Earth view. And that's good news because that means your radio propagation is looking wonderful. And now you GPS users, well, you know, we don't have any big solar storms on the Earth's night side to bother you. And we don't have any big solar flare players that are giving you big radio blackouts. So believe it or not, the space weather conditions and your GPS reception pretty much all over the globe should be top notch. I'm Tamitha Skov, the Space Weather Woman. Thank you for watching.
So if you've not heard of her before, you can find her information. I'm trying to get my mouse back again. I'm on multiple screens here. There we go. Here's some links that will work. And what I found fascinating was that it was just like the local weather forecast on the TV station, but it's all space weather. And from what we've gone through tonight, a lot of the things that she talked about fit right into the things that we discussed tonight. Solar wind, solar storms, propagation, all of that. So just really, really wonderful stuff. And that's everything that I had for you tonight, including the bonus material at the end. I'm glad we had time for it. And next week, what are we going to do next week, Gary?
Well, next week, we'll be doing safety. And it shouldn't be the last chapter in the book. It should be the first chapter, but okay. And I'm going to do my best to convince you that ham radio is an adventure. So we'll do safety in the first half of the class next week. Then we'll take a break. And then we'll come back and take a 35-question practice test together. You'll score your own test, so we won't know how you're doing, but you'll know how you're doing, and you'll know how we did. So that's next week.
Right. So I didn't ask if there were any questions at the end of what we talked about tonight. So we'll open it up for questions at this time. And if there aren't any, we'll wrap it up for the evening a little early. Everybody looks like they're ready to go home, but you're probably already home, so. doesn't
Their
matter.
brain is expanded.
What was that weather space thing website?
Spaceweatherwoman.com. If you Google on that or go to YouTube, and it's also going to
I
be in
put a
the.
link.
It'll be in
There's
the
a link in the chat.
Yeah. Oh, there's a link in the chat, and there'll also be a link in the PDF that Gary sends out tomorrow. All right. Anything else? Well, I hope tonight was fun and encourages you towards some things you can do in your future ham radio career. You want to get started just by getting your license, of course, and then put your toe in the water on some of the easy things to do to get started, and then advance into some of these other things.
You're almost done.
Almost done. Yep. Next
I
week
want to
is.
thank everybody in your staff.
No
yeah.
problem.
We love doing this. And we're very excited.
Great job, guys.
Yep, you betcha.
All right,
You
so
betcha.
we'll say 73 and
Yep.
see you next
Thank
week.
you.
You bet.
Thank
73.
you.
Bye, everybody.
Dave,
Yeah.